Thank you, Tiffany. Kia ora koutou. Welcome to the first of the series of seminars for the Biosecurity Bonanza. Today's speaker is Dr. Dave Latham. Dave is a wildlife ecologist with Manaaki Whenua, based here at our Lincoln office. And the topic today is wallabies. Bennett's wallaby were introduced to the South Island in 1874 for hunting, and they've spread and they now cause significant damage to the environment. So today, Dave's going to discuss recent research on wallaby management in Canterbury, but within the broader context of wallaby management in New Zealand as a whole. So I will pass over to Dave.
Thank you very much, Graham. Good morning, everyone. Thank you for attending this talk. As Graham has just alluded to, the title of this talk is Research Needs for Effective Wallaby Management in New Zealand. That's a pretty big topic, so I won't be able to cover all of that today. So instead, I've decided to talk about some research that we've done recently on Bennett's wallaby. And so I put in a subtitle, Management of Bennett's wallaby, Having Confidence in No Detections. So that relates to the eradication strategy in place for wallaby in the country currently. And hopefully that subtitle, and specifically having confidence in no detections, becomes apparent as I work my way through the talk. So I'd like to start by acknowledging my co-authors here, Dean Anderson, Rochelle Binney, Simon Howard, Cecilia Latham, and Bruce Warburton, all from Manaaki Whenua. We received a lot of other support as well, and I'd just like to go through those quickly. Waitaki Wallaby Liaison Group, MPI Sustainable Farming Fund, Environment Canterbury, Otago Regional Council, and Manaaki Whenua for providing funding support. I'd like to thank the owners or managers of the properties that allowed us to do the research. So that's John Aberlin from Glencarry, Tom Bell from Blue Cliffs, and Guy King from the Grampians. Corrie Tigalars and Halley Ventures New Zealand captured the wallabies for us. Ross Chilton and Lloyd Brown did the ground surveys with the dogs. The late Grant Halverson and Jordan Munn did the thermal imaging camera work for us, and Brent Glentworth from Environment Canterbury provided logistical support and feedback on numerous things for us. So that was, we really appreciate all of that support. So as I say, the topic today is going to focus on some research that we did with Bennett's wallaby, but the research objectives that I'm going to discuss today are relevant for all of the species of wallaby in New Zealand. And they're actually relevant to many of the eradication initiatives that are going on in the country currently. So, as Graham has just told you, Bennett's wallabies were liberated in the Hunters Hills in the South Island in 1874, primarily for hunting. They established and became invasive, and I'll show some distributional slides in a second. And as most folk will know, they had unwanted impacts in production landscapes and on native vegetation. So here's a map showing the distribution of this species of wallaby. You'll note that there are various coloured polygons in this black polygon, which delineates the containment area that Environment Canterbury have come up with to manage Bennett's wallaby. And you can see how the wallaby has spread over time up to 2015, which is when this work was done. By and large, the population is confined to the containment area, but there are a couple of small populations that have been known for a while outside of the containment area. One at the northeastern end of Lake Tekapo, and sorry, that's Lake Tekapo, and one just south of the Waitaki River. And that core range equals about 5,300 square kilometres as of 2015. But there have been numerous wallabies that have been shot outside that area and confirmed sightings as well. We're not really sure about the status of some of these point locations, but it's likely that many of them represent what we term low-density peripheral populations. And if we include that information up to 2015 again into the range of Bennett's wallaby, we're looking at more like about 14,000 square kilometres occupied by that species. These outlying populations are key starting points for eradication. So remove these locations and work your way back into the containment area. So if we look at that a little bit further, this work represents what they are predicted, where they are predicted to be in 50 years' time if we don't have intensive control to reduce that rate of spread. And that area out to the edge of the blue polygon is in 2065, and it represents about 44,000 square kilometres, so quite a large chunk of the South Island. So it's pretty important that we do something about that. And recently there has been the National Wallaby Eradication Program that has been set up to try and prevent this spread of not just Bennett's wallabies, but Dama in the North Island, and to manage ultimately the wallabies on Kowal Island too. And as the name suggests, the strategic objective is eradication of all species of wallaby from New Zealand. So this objective requires a tool to guide how much survey effort is needed to have confidence that a targeted wallaby population has actually been eradicated. So what do I mean by this? So if one or more wallabies are seen after an eradication attempt, it was clear that eradication was not achieved, and additional work is needed to try and mop up the survivors. But what if the target area is surveyed and no wallabies are seen? Is it because there are no wallabies present, or wallabies are present, but they were just not seen? So this brings us back to the subtitle of the talk, having confidence in no detections, which is critical for eradication. So having confidence that no detections equals no wallabies is critical for eradication. If we stop in our eradication attempt too early, it will allow survivors to recover the population. And if we stop too late, it can mean that we waste a lot of funding that could be spent on other populations, removing other populations. So this brings me to the objective of this particular work, and that's to determine detection probabilities and surveillance sensitivity for a suite of survey methods for proof of eradication modelling. So there's a bit of jargon in there, and I'll try and work through that carefully. But there are 2 points I want to mention firstly. When I talk about detection probabilities, it differs to some people's concepts of what the work is about. We did not compare the relative effectiveness of different detection methods for sustained control or kill rates achieved or anything like that. And we assessed detection probabilities, not detection rates. So detection rates enable us to determine how well one survey method performs compared with another method or over time. In other words, they're relative measures. It does not inform us about the number of wallabies that are not detected, and that is a critical piece of information for eradication programs. However, if a method has a high detection rate, its detection probability will also, on average, be high. So, last couple of bits of jargon. The probability of detection is the probability of a survey method detecting a specific individual, given that the individual is present in the detection range at a specified time. And the surveillance system sensitivity is the probability that multiple survey devices or search paths will detect a specific individual, given that it is present anywhere within the total area of interest. So in essence, the surveillance system sensitivity is using the probability of detection and scaling it up to the area of interest. So we determined detection probabilities for a suite of commonly used methods, as well as some reasonably recent technology. So a ground hunter with dogs, helicopter observers, helicopter with a thermal imaging camera. Now I'd just like to pause on this helicopter with a thermal imaging camera quickly. We used that camera in the helicopter in a fixed position. Many operators of thermal cameras would argue that that camera should be hunted with. So in other words, the operator points the camera manually in the habitats that they believe are going to be best for wallabies. In our case, we couldn't do that. We needed to know the area that was searched by the camera. And when you move that camera around, there's no technology currently that will enable you to work out how much of the area you have actually covered. So we were constrained to keeping it in a fixed position and flying at a fixed height above ground level. That's one of the limitations of the work, and I'll come back to that at the end of the talk. And the last method that we looked at were camera traps deployed on the ground. So we used the detection probabilities and search effort to estimate surveillance sensitivity for each survey method and used this information to develop a proof of eradication model. But how do we estimate detection probabilities? We need to know how many animals were in the area of interest. And we also need to know how many of these were detected. And this is critical information because it gives us the detection probability for each survey method. But estimating N or the total number of animals in the area that you're surveying is difficult for wild populations. The estimates are usually quite fraught with error, and this can affect subsequent results. So it's very challenging. So our approach to get around this was to capture wallabies and deploy a GPS collar on them that took a fix at 5-second intervals. So it gave more or less complete track file from that animal. So this method provided us with a known N for potential detection, that known number of marked animals that we had there. This picture, if anyone's interested, is one of the methods that we use to capture wallabies, a ground net on, and yeah, it would close up on the wallabies and we'd capture them and deploy a GPS collar on them. So we knew how many animals could have been seen when the helicopter flew by or the ground hunter walked by, and we could compare this with how many animals were actually seen for each, marked animals were seen for each survey method. This is one of our GPS collared wallabies. So on to some results. So we captured and deployed collars on 38 wallabies, and 30 of these provided usable GPS data. So this first table here, there are a couple of things I'd just like to point out to begin with. This only relates to collared wallabies seen, not wallabies in total. It's also only for the mobile survey methods, so the ground hunter, the aerial observer, and the thermal imaging camera. The camera traps, the detection probabilities have to be estimated in a different way, and I'll bring that in towards the end of the talk. But for the meantime, we can only focus on creating a comparable design for the mobile methods. Now, each survey method was run more than once, so there were multiple surveys that were done. It's also important to note that some of the collared wallabies could move out of the study area when the survey was done, so not were all available to be seen by the survey methods. And each of the mobile surveillance methods had a different field of view, which again complicated things. But nevertheless, the take-home message here is that from the work that we've done, the ground hunter with the dogs had a higher average probability of detection than either of the aerial methods. Now, I mentioned I wasn't going to get into detection rates, but this slide shows this. So this is again the same information from the previous slide with the probability of detection for each of the three mobile methods. but I've also put down the total number of wallabies that were seen. So this isn't just collared individuals, it's all wallabies. And I just wanted to put this in to show that the thermal imaging camera actually did detect quite a few wallabies, not only a few less really than the ground hunter. But once you bring search effort in, we found that the number of wallabies seen per kilometre surveyed was actually quite low for both aerial methods compared with the ground hunter. Again, because a helicopter can cover ground far faster than a ground hunter can. So if I get onto the surveillance sensitivity for the mobile methods, that's taking this information that I've just presented on the detection probabilities, and it's also using search effort, so the coverage that each method can achieve. So the first thing to note is for surveillance system sensitivity, the results can vary between 0, which is quite insensitive, to 1, which has perfect sensitivity. Now, the next thing is that we had to standardize the results for each method. This is because they had different swath widths associated with them, and we needed to make each method comparable. So to do that, we standardized it to a 1 kilometre search transect and applied that within a hypothetical 100 hectare survey area. And so again, the take-home message here is that once you do that for this 1 kilometre search transect, the ground hunter has higher surveillance sensitivity than either of the aerial methods. So if we scale that up now and apply it to probability of wallaby absence in this hypothetical 100 hectare survey area, assuming no wallabies are detected, we can see the results here, and I'll try and talk you through that now. So we have the 3 mobile methods here, but I've also brought in the camera traps into this table. The way that the information for the camera traps is calculated is a little bit different, so I'll talk you through that as well. So to get full coverage of this 100 hectare survey area, the ground hunter requires 5 transects, 5 of the 1 kilometre transects to get full coverage of that 100 hectare survey area. The aerial observer requires 4, the thermal imaging camera 10, and that's because, as I say, the swath width for each method varies. For the camera traps, it was a little bit different. We didn't survey that 100 hectare area using swaths, but rather we deployed 16 cameras on a grid of 300 meters by 300 meters, and we left those cameras in situ for 80 nights. And so that represents 1 single survey for each of the methods. So 1 survey for a ground hunter was 5 transects, and based on that 1 survey, the surveillance sensitivity for each method can be calculated. And so for a ground hunter, it's 0.45, aerial observer 0.13, thermal imaging camera 0.2, and camera traps 0.82. So again, the camera traps and the ground hunter, based on this, are a little bit higher than the aerial methods. Now, obviously, when we talk about eradication, we want to have reasonably high confidence, and we talk about quite frequently a 95% probability of absence. So how many surveys need to be done to reach that 95% probability of absence? So for a ground hunter, it's 5 surveys. For an aerial observer, it's 21. For a thermal imaging camera, it's 14. And for the camera traps, again, it's a little different. So we have decided that for the camera trap placement, they be left in place for 160 nights rather than 80 nights. Alternatively, you could deploy more cameras into that 100 hectare survey area, but that would require purchasing more cameras, deploying them, servicing them, etc. So we think that the easiest option might be just to leave them in place for a longer period of time. So onto some costs. These are just indicative. It's based on our work. It's highly likely that the overheads associated with different agencies might differ to what we incurred, but nevertheless, this should provide some sort of a guide. So we have each of the three mobile methods in grey, and I've highlighted the cameras a slightly different colour because the cost associated with cameras have to be calculated in a slightly different way. I'm not going to go through this in great detail, but we incorporated speed and swath into the mobile methods, dollars per hour, hectares per hour, dollars per hectare can then be estimated. From the previous slide, you can bring in the surveillance sensitivity for each method. We want to get up to that 95% level of confidence. And then from the previous slide, again, you can bring in the number of repeat surveys that are needed to get to this 95%. And based on that, you can estimate the cost per hectare for each method. In this case, the ground hunters with dogs came out quite a lot cheaper, followed by the camera traps, and the aerial methods were a bit more expensive, as you would expect when you're flying a helicopter. Now, I just want to point out for the thermal imaging camera, as technology improves, that cost should be reduced. So as the quality of the camera gets better and cameras become more affordable, we can actually fly at a higher level above ground. That will increase the swath width for the thermal, and that will significantly reduce the cost of that method. At the moment, that is one of the limiting factors. You have to fly at a reasonably low level. It creates quite a small swath. You'll note it's 1/3 that of what the aerial observers can see. If you can increase that swath, it's going to decrease your costs per hectare. So it should only get better. So I've got a slide on limitations here. So we developed a surveillance protocol for proof of eradication modelling for Bennett's wallaby. This model needed quantitative empirical data for each survey method, but there were scientific constraints that may have biased some survey methods, and especially, as I've alluded to, the thermal imaging camera. Not only, we also had some problems with the ground hunter with dogs and the aerial observers, but we think that the thermal imaging camera was probably a little unfairly constrained by our scientific requirements. So as I say, one of the big ones was that we couldn't hunt with the camera. We had to keep the camera in a fixed position to have that known swath width. And so that's was a very large limitation, and it's a key research need when that technology permits to try and work out exactly what the size of the swath width is when you hunt with a camera. And also using thermal imaging on a UAV or a drone is another research need. We've trialled this for Environment Canterbury. However, the interesting thing there is that in most instances, if you use thermal on a UAV, the camera is in a fixed position anyway, so it's actually quite comparable to what we did for the helicopter. So, summary. The ground hunters with dogs and the camera traps performed well, but both are quite hard to scale up to a very large area, especially what is needed for eradication of Bennett's wallaby or Dama wallaby from the country. Unless we can get a very large pool of hunters and dogs, wallaby dogs, or if we can acquire a huge number of camera traps and field staff to deploy and service those. So it's pretty logistically difficult to cover large areas with those two tools. And I think this is where the aerial methods may be highly effective, even though they'll be costly. So the detection probabilities and surveillance sensitivity were lower for those aerial methods. They were more expensive per hectare, but to cover these very large areas within the required timeframes, we think that they probably will be necessary. So methodology that I've laid out here today is critical for achieving wallaby eradication, giving managers confidence that an area that they've applied management to has actually had the wallabies removed from it. But we do need better and more data for parameterizing the proof of eradication model. And some of this work is proceeding currently, but we certainly need better information for the thermal imaging camera operated from both a helicopter and a UAV, and we need it for other species of wallabies as well. So I'll finish there. Thank you.
Thank you, Dave. We've had a number of questions come in, so that was an interesting presentation, and we'll turn to the questions for a little bit. First off, let's see. Okay, is this study based on a single habitat type? In other words, would the methodologies have different results in different kinds of habitats, such as open country versus scrub versus forest?
Yes, different methods will be affected by those, and we did look at that. Unfortunately, I think, so we've, just to make people aware, this work is currently in review with a journal. It's in the final stages of revisions. We hope that'll be accepted, and if anybody's interested, I can certainly pass that on to them. In that manuscript, we cover the effect of habitat, and certainly we know that different methods are going to be more suited to different habitats. For example, an aerial observer will be more likely to see it in wallabies in open tussock country than they will in dense forest. The thermal imaging camera operates quite well through forest if there's a good open canopy gaps and a nice cool forest floor. Camera traps don't work quite as well in areas where you've got a lot of vegetation that can blow. So in open tussock, for example, you'll end up with a huge number of photos of blowing tussock. So yeah, certainly it does depend on the habitat, and I didn't go into that here today. Unfortunately, to a certain extent, as we split things into a number of different habitats, our sample size can start to compromise things to some extent. So I think that in subsequent studies, that is something that we will try and get a bit of a better handle on.
Okay, thanks for that. Okay, another question. Did you use just one hunter with dogs for testing probability, or a range of them? I can imagine there might be quite a lot of variation in detection probability depending on the hunter and or the dog.
Yep, I'm sure that is the case. We used two guys that had been trained for this specifically. Environment Canterbury uses both of them all the time. We found very little difference between them. However, I mean, I would agree entirely that particularly if for management, an agency wanted to scale up and cover large areas with a ground hunter and dogs, and some of those staff had received little training, that the detection probabilities would vary greatly. That would require a slightly different study in which you might compare those ground hunters with dogs who had a lot of experience versus those that were new into the area of, into the industry, I guess. So, I mean, yeah, certainly that will be another level of variance that could come into it.
Thanks for that. Any evidence that some individual wallabies were consistently detected by one method more than another? So would a combination of methods give more confidence than using just the most cost-effective one?
The first part of that's quite interesting. I don't think we actually looked at that, whether some wallabies were consistently detected. Certainly we would advocate in some habitats for some areas that more than one method was used. So I think that's a very fair point. And we have created a online tool which will be refined over the next few years, and that tool has the capacity to look what your bang for your buck would be incorporating more than one survey tool into your surveillance strategy.
Thanks for that. Another question just came in. Let me read it. Identifying that there are wallabies in a given area doesn't necessarily involve having to actually see the wallaby. Have you done or planning any work on methods for example, scat detection to identify areas of interest or determine success of eradication?
That's a fair enough point. We have just been asked to do some work for MPI and Bay of Plenty, who often use a dog handler with detection dogs to find wallaby scats. And so we will be looking at that in the next little while, but certainly that is part of it. It's not necessarily just looking for live wallabies, no.
Okay, thank you. Is there a camera trap that uses heat and movement detection versus just movement? That might eliminate the problems with things like tussock movement.
Yeah, I mean, I guess there's all sorts of cameras available. We used a number of different cameras and we corrected for those, but we found that some reduced the vegetation down much better than others. They also tended to be the most expensive. So I guess that's kind of the trade-off there, is that the better quality camera that you get, you're likely to pay a lot more for it. So but certainly camera make, model, and does affect it, yes.
Okay. How well does aerial imaging distinguish between possums, deer, pigs, and wallabies?
It's highly effective as long as you get a good view of the animal. There are instances in which you might get a small fragment of what looks like an animal, partially obscured by vegetation, but I guess all of the methods have some form of limitation, and that is potentially one of the limitations of thermal imaging, that you just can't see through very dense vegetation. But otherwise, I mean, it is very clear and very obvious that it is a wallaby.
Okay, I'll just take two more questions and then we better wrap up. Firstly, is eDNA being used to detect evidence of wallabies, I guess, over the broader areas?
There are people that are looking at using that tool. I'm afraid I can't comment on the status of it, but if anyone is interested in that, we do have colleagues in Landcare that are interested in that space, so I can certainly put any interested people onto experts if they would like to discuss that further.
Okay, and I should say that we can follow up on questions. Final question, did you learn anything interesting from the collared wallabies that you weren't expecting? For example, range of movement, etc.
I think that there had actually been surprisingly little work done previously on wallabies to begin with. I don't think anything came out of this work with regards to movement or home range size or anything like that that was particularly surprising. The wallabies tended to use those habitats that previous studies have suggested they do. And yeah, their movements were pretty much from pasture margins and back into forested or tussock cover. So no, there was nothing particularly surprising in that regard.
They just did their wallaby thing.
They did their wallaby thing, yes.
I think that's it for questions. So thank you very much, Dave. And
that's okay. Thank you very much.
I'll invite everybody to return the same time tomorrow for the second in our series, which will be Grant and Aubrey talking about the use of misinformation to fool predators to protect rare birds. Thank you for joining us.